Hi, in this video I'm going to be talking about a couple of different ways to communicate differences between two population proportions. Up till now, in the previous sections of this unit, you've seen where we will study the difference P1 minus P2 between two populations. And instead we're going to study this same idea but using fractions. And the two different ways we're going to study the difference between two groups here is relative risk and odds ratio. So let's get started. The first method is called relative risk. And instead of measuring the difference between two population fractions, what we're going to do right here is define a fraction of the two population proportions called RR, or relative risk, and it's the population fraction in population 1, P1, divided by the fraction that's in population 2, P2. And what we do to study this from sample data is we take the sample fraction from the first sample from population 1, P hat 1, and we divide it by the sample fraction from population 2, P hat 2, and of course if populations are equally frequent and have equal population fractions, when you divide equal numbers by each other you get a ratio or a fraction of 1. So what I'm saying here in the third bullet is that if a relative risk is 1, it means that the first population has exactly the same risk of event as population 2 does. So in this case, a fraction, a relative risk of 1, is equivalent of saying no difference between the two populations. If you get a relative risk that's bigger than 1, like here in this first bullet, it's got to mean that the fraction in population 1 is bigger than whatever it is in population 2, if the fraction turns out to be bigger than 1. Relative risk bigger than 1 means first population more frequent, more likely to have an event than population 2. And likewise, if the relative risk would be less than 1, it would mean the first population has less risk than the second one. And here's an example from a study earlier in the course, the Physician's Health Study, that was only done on male doctors. Remember that there were two treatment groups here, whether the physicians were taking baby aspirin every day, and there were 104 heart attacks out of over 11,000 doctors that were taking aspirin, and that gave a p hat of like 0.009. And then there was the control group, or the placebo group, and there were 189 heart attacks out of about 11,000 subjects there for a p hat of 0.017. If you make the estimated relative risk of placebo group p hat divided by the aspirin group's p hat, you get a relative risk estimate of 1.82. And that is above 1, suggesting that the placebo group in the numerator, that population, has a higher risk of heart attack than the aspirin group. And what you would say here is that the placebo group, the way you interpret this number, is the placebo group has 1.82 times additional risk, or times the risk of a subject on aspirin. So almost twice the heart attack risk of someone taking aspirin. You can analyze this kind of data in R and RStudio with a package called BStats, or biostatistics package, and then there's an odds ratio function in that package which will calculate these relative risks for you. You put in the number of events in a list like we've been used to doing: 189 heart attacks for placebo, 104 for aspirin, total number of subjects for placebo 11,034, for aspirin 11,037, and down here on the bottom we get the estimated relative risk of 1.82, and we get a confidence interval, lower limit and upper limit for the confidence interval of 1.5 up to about 2.2, And the important thing here is that that entire confidence range for the population relative risk, whatever the real underlying relative risk for the comparison is above 1. So the where's Waldo Wally moment here is where's 1, and 1 is not contained in this confidence interval. All of the reasonable values for the real relative risk are bigger than 1. And so that means evidence that the placebo group has higher heart attack risk than aspirin, or in other words, aspirin reduces heart attack risk. And that would be the conclusion from this study. Another way to compare two population proportions are with a concept in a computation called an odds ratio. And in order to talk about odds ratios, I suppose I should define odds for you. Odds is a fraction, and it's the probability of an event happening here in the numerator, designated by the symbol p, a population proportion, that had the event, and then the denominator of odds is the probability that the event doesn't happen. So if an event is equally likely, like a coin flip, remember, has a probability of being heads of a half. That means it has the probability of not being heads, tails, also of a half, and a half divided by a half is an odds of 1. So something with even odds means that it's equally likely to happen or not happen. If an event is very, very unlikely to ever happen, that is a p of about 0. And notice that the odds would be 0 over 1, and a very unlikely event would start to have odds approaching 0. A very, very likely event would have a chance p of about 1, so the numerator would be about 1, and the denominator would start to get closer and closer to 0, and that would mean you're starting to divide by something that's near 0, and it would mean the odds are exploding off to almost an infinite odds. So bigger chance means odds is bigger. Smaller chance means odds are nearer to 0. And that's the idea of odds. And you can compare two populations through a fraction, a ratio of odds called an odds ratio, OR. And the way it works is a little bit like relative risk. If you have an odds ratio that's equal to 1, it means that the risk of the event happening in the first population is equal to whatever it is in the second. And so there's no evidence of a difference. There's no difference between the risk in one population and another if the odds ratio is 1. If an odds ratio is bigger than 1, it must mean that the first population has a bigger risk of the event than the second. If an odds ratio is less than 1, it must mean that the first population has less risk than the second one does. And you can estimate it from sample data using estimated odds from the two populations, which is made out of the estimated p-hats from the two populations, p-hat 1 or p-hat 2, to make the odds in the numerator and denominator. And you can make an estimated odds ratio. So here's an example to illustrate. We, of course, have data from Australia, cannabis use, and this is studying cannabis use in men. There were 169 men studied, and 117 of them were cannabis users, and that makes a p-hat over 1 minus p-hat of about 2.25. The p-hat, of course, is 117 over 169 for the first group. For women, it would be 43 cannabis users divided by 167 total women, and that makes an odds of 0.35. When you divide the male odds by the female odds, you get 6.49, and that means that males are about 6.5 times more likely to be a cannabis user than women are in Aboriginal communities in Australia. If you use RStudio and R for this, the odds ratio function gives you the way to put in the number of male cannabis users, events, 117. The number of female cannabis users, 43. The sample sizes of men, the sample sizes of women, and you get the odds ratio section right here. Estimated odds ratio 6.49. Lower, lower limit. We'll do the asymptotic one, and we'll get a lower boundary for the odds ratio of 4.31 and upper boundary of 9.77. And the big thing to notice here is that the confidence interval is all entirely above 1. Remember, 1 means no difference between the two populations. And so since this confidence interval doesn't include 1, it is very clear that there is a difference between male and female risk of using cannabis. And the way it works is numerator was men divided by denominator population, which is women. So very clear evidence that the odds or the risk of cannabis use is bigger for men than women. And that is the end of the notes for this section. What I'd like you to do now is go on our course Moodle under the topic called Inference About Proportions, and open up the research articles Indigenous Substance Use, again about Australia. Open up Soft Drinks and Hyperactivity in Norway, and open up the document Violence at Convenience Stores. And let's take a look at the Indigenous Substance Use article first. This article is from the journal Drug and Alcohol Review in 2004. There was a study of cannabis and substance use in the Northern Territory of Australia. And if you take a look right at the very beginning at the abstract, you'll see some odds ratios in here and some confidence intervals. Let's try to understand what's being done here. So, for example, right in here in the middle, they present results about lifetime cannabis use. So, lifetime cannabis users, it turns out that 69% of males and 26% of females were lifetime cannabis users, and the odds ratio of male to female, because they listed males first, then females risk, and then they give an odds ratio, and that's telling you that it's males in the numerator and females in the denominator. That odds ratio is 7.4. That would mean that males are about 7.4 times the risk of being a cannabis user in their lifetime compared to females. So a very substantial increase in risk of cannabis use for males than females. And right next to it are the confidence bounds, and you can see that those confidence bounds for the underlying true odds ratio are clearly above 1. Talking about current cannabis use, they give you the fraction for males, the fraction for females, and the odds ratio of 7.9. And so males are 7.9 times more likely than females to be a current cannabis user. Confidence interval 4.8 to 13.1. And so this would be a way to understand that there is a difference in risk between males and females, and you will frequently see odds ratios reported like this with confidence intervals, and you can also see p-values there as well. For the soft drinks and hyperactivity in Norway, scroll in the article to table 3 and you'll see some odds ratios in here. So for example, what this would mean is that let's take a look at consumption level of more than 4 glasses of soft drink per day. That would define the numerator of an odds ratio, and the denominator, the reference level, is what is denoted here as reference. So the comparison group or the comparison population in the denominator is if you drink 1 to 6 glasses a week. So it's a lot of consumption per day. Somebody that's drinking a lot of soft drinks per day, more than 4 a day, relative to those that have moderate consumption, 1 to 6 glasses a week. The odds ratio for mental distress, the event being mental distress is 2.95 times greater for the big consumers relative to 1 to 6 glasses a week. Notice the confidence interval right here is entirely above 1. It is very clear that higher soft drink consumption is related to increased risk of mental distress for the high levels of consumption for boys. If you look at hyperactivity, it's over 4 times more likely for high consumption levels rather than 1 to 6 glasses a week. Confidence interval all entirely above 1. Same with conduct problems, total difficulties. So you can see the high levels of soft drink consumption have clearly higher levels of trouble than the reference group 1 to 6 glasses a week. You'll notice when you compare 1 glass a day to 1 to 6 glasses a week, the odds ratio is a little bit nearer to 1.22 times higher risk than 1 to 6 glasses a week. And the confidence interval includes 1. So it's not significantly different, the population that has 1 glass a day to having 1 to 6 glasses a week. There's just not enough evidence to tell those two groups apart according to mental distress. But for something like hyperactivity, it is statistically clear that 1 glass a day has higher risk of being hyperactive than 1 to 6 glasses a week, because you can see the confidence bounds include only values above 1, and the point estimate for the odds ratio is about 2, so about double the risk of hyperactivity for just this additional amount of consumption, 1 glass a day, compared to 1 to 6 glasses a week. And you can see similar table down here for girls. Crude odds ratios are the things that I have been describing in the notes, just an odds in the numerator divided by an odds in the denominator. The sections of the table that are called adjusted odds ratios are from some more sophisticated statistical models that you would take in a second course in statistics at UMM Data Analysis 3601. The final article is about violence and retail stores. Please move ahead to Table 2 in the article, and it shows table outcomes for relative risks, in other words, risk ratios. And the way you will read Table 2 is there is a relative risk being constructed, and the numerator of the first relative risk, 1.64, where does that come from? It comes from the numerator p hat. If anyone in the store resisted, what fraction of those events had an employee injured? That would be a p hat of 348 divided by a sample size of 1086. There were 1,086 events or instances where someone resisted, and out of those 1,086 times, 348 resulted in an employee getting injured. There were 800, and the denominator is out of the 873 sample size where there were nobody that resisted during the event, 192 times the employee got injured. So it's a ratio of p hats. 348 divided by 186 in the numerator, p hat 1, divided by 192 divided by 873 in the denominator made a relative risk, a risk ratio of 1.64. And it means that if anybody resists, it is 1.64 times as likely that an employee will get injured relative to the risk when nobody resists. So there is an increased risk of an employee getting hurt when there is confrontation and there is a resistance to the robbery crime. Notice the confidence interval for the relative risk is entirely above 1. This is statistically clear that anybody resisting leads to increased employee risk in such cases. If you want to think about the event of whether a customer gets injured, that relative risk is 1.4 times additional risk of customers getting hurt if there is resistance to the crime. Confidence interval is entirely above 1, suggesting that anybody, the population of events where anybody resists has higher customer injury risk than if there's no resistance. Notice on some of these, for example, if there's a perpetrator that is using alcohol, notice there is clear statistical evidence of increased injury risk to an employee. Confidence bounds above 1, 1.7 times additional risk for an employee to get hurt. Notice, however, that there isn't any evidence that customers are at increased risk of injury when the perpetrator is using alcohol. Evidently, when there's alcohol involved, the perpetrator is concentrating on the employee and is less concerned and distracted by customers, and just not as much, no evidence that they're having customer injuries. And this would be the way you would read a table like Table 2. Please let me know if you have questions about reading tables like this for odds ratios or relative risks, or any of the formula content. You'll have problems like this on your midterm and final exams, so make sure you try to get things cleared up if you have questions about what's happening.